Okay, let's find the derivative of the integral from 0 to x cubed sine of 1 over t dt. The first thing we want to notice is that there are two anomalies here. The first one is that the sine is not a function of simply t, it's a function of 1 over t. You know what? That doesn't even bother me. That's just a definition of this inner function f of t. Don't worry about it. Instead, let's think about the upper limit on the integral not being simply x. In the fundamental theorem, we are accustomed to seeing a number for the lower limit on the integral and then just simply x on the upper interval. That's not what we have here. We have x cubed. So since we have the integral from t equals 0 to t equal x cubed, we're actually talking about finding the derivative here of a composite function. And anytime we take the derivative of a composite function, which here I'll call it g of x cubed, I have to use a chain rule. So here's a two-step answer. Step one, I'm going to demonstrate that the inner function f is continuous. Well, f of t is equal to the sine of 1 over t. And we know the sine in general is going to be continuous for all real numbers. We really are interested only on the interval from x values from 0, the lower limit, to infinity. But here we have more than we need. We have all real numbers. Well, if the sine of x is continuous, the sine of 1 over x is going to be continuous. So the sine of 1 over t is continuous everywhere, and we can use the fundamental theorem. That's what we're going to do in step 2, apply fundamental theorem using the chain rule. So the derivative with respect to x of the integral in question, 0 to x cubed, of the sine of 1 over t dt is equal to the inner function sine evaluated at x, so it's 1 over x cubed, evaluated at u, which is x cubed, and then times the derivative of x cubed, which is 3x squared. So our answer is 3x squared times the sine of 1 over x squared. Now I'd like you to try that. Let me bring this down and I'll make the screen larger and give you a you-try problem. You try to find the derivative of the integral from -2 to x squared of the polynomial t squared plus 5t plus 4 dt. So go ahead, you're going to use step 1 and step 2, but pause the video, try to work it out, and come back and restart to see how you did. All right, you're back. I hope you got it. Let's do this. Step 1, show that the little function f of t is continuous. Well, little f of t function, the second thing we'll do is apply the fundamental theorem. Little f of t is t squared plus 5t plus 4. Well, the fact is that that is simply a polynomial. And we know in general the polynomials are going to be continuous for t element of any real, all the reals, any real number. So t squared plus 5t plus 4 is continuous everywhere. So therefore it is continuous from the lower limit -2 to infinity. Step 2, apply the fundamental theorem. Well, since it appears the upper limit is not x, it's x squared, our function is not a function of x, it's a function of x squared. So the integral from -2 to x squared of t squared plus 5t plus 4 dt is equal to the evaluation of the inner function, little t squared plus 5t plus t4, integrated into x squared. So x squared squared plus 5x squared plus 4 times the derivative of the upper integral limit x squared gives us x to the 4th plus 5x squared plus 4 times 2x. And then we can distribute multiplication to get 2x to the 5th plus 10x cubed plus 8x.